Space news roughly covering the last month. Let me start right off with, can anybody guess what this is? Now, it may look like an ashtray, but I can assure you it's not. You don't need an ashtray in outer space. There's not much demand for that. Well, it is. 50% credit. Yes, it's a telescope. Specifically, it's the Euclid Space Telescope that was just launched during this last month. This is put out by the European Space Agency, although it's interesting that originally it would have been on one of their own rockets, but, well, their own rockets, meaning a Russian rocket, but since we're not dealing with the Russians anymore, they ended up having a launch by SpaceX on a Falcon 9. Now, why is it there? This is a telescope, but it's kind of unique. Well, it is focused on optical and also near infrared, but for a particular reason, and it's focusing on dark matter and dark energy. Now, what's that? Well, there's a problem. The scientists basically say they can't really find 95% of the matter and energy that they think is really in the universe. That's not a very good record. You know, they can tell it's there. I mean, you basically say that you have indirect observations. For instance, if you have a large mass, it bends the space around and it bends light waves that go around objects. It's called gravitational lensing, and you can see that. And there are a lot of places where they can see that there's just not enough matter there to account for the gravitational lensing that's occurring. So that tells them there's something else there. But really, the whole thing of what is dark matter, fundamentally, they don't know. And that what they want to do is they want to get a lot more observations, figuring out, well, where are all these concentrations of the mass that we see indirect evidence of but can't quite explain. So, no, they don't really have an explanation. And it's worse than that, because based on all, even just the mass that we know about, the universe is expanding. It should be slowing down. That expansion should be slowing down. But it's going the other way. It's actually expanding faster. It's accelerating. And so, well, that doesn't really fit any theory we have right now very well. So they made up a word for that called dark energy and said, okay, dark energy explains it. But of course, nobody really knows what it is. But that's why you have the space telescope. The problem is this 95% being gone is very annoying to scientists. If you're a scientist, this is extremely annoying. It's just embarrassing. I mean, imagine if you were a banker and you could only account for 5% of the money in your bank. Okay, that's a bad example because actually banks have 5% reserve requirements. That is actually all they have. The rest of it's kind of indirect. Yeah, okay, you could say you might suspect that the model is fraudulent, but they just say it's incomplete. And that actually is the way that science normally progresses. You say, I got some equations that describe the universe. Here's what we think it is. But when you're off by 95%, it's just embarrassing. So they want to do something about that. So step one, they've already taken. We said that you call it dark matter and dark energy. So you give a name to it. And that's got a long history. That's not just science. I mean, the medical world, when there's something like a sudden death syndrome or something of infants in cribs, or there's somebody's syndrome, you make up a name for something. You give it a name. And then you can start writing papers. You can make up theories. You can have conferences, all focused on that name. And that's how it works. But eventually you end up funding new experiments. And you test out the theory. With new observations from experiments, you can rule out a lot of those. And the ones that are left, those are the ones that are probably the best bet. So we're at that early stage here. The Euclid Space Telescope, what it will do, it's going to map in 3D about a third of the universe. They're also, because you're looking at stars' light that came from many, many years ago, you're looking back in time about 10 billion years. That's about as far back as they go. But they're hoping to discover answers. It really is a data collection exercise, trying to figure out where is all this dark matter and energy, and try to explain it better, because they just don't really have a good idea right now. I sound like I'm making fun of it, but actually this is how science works. You basically recognize that your existing theories that explain things are doing a lousy job, and you try to figure out, well, make up some ideas, well, why is that, and then test them. And that's what's going on here. That space telescope is to do that. So where does it go? Well, it's going to go out what's called the Sun-Earth L2 point. And what that is, imagine if you're standing on the sun and you look out to the Earth, well, and you don't get fried in the process. And you look beyond that. The L2 point is way beyond Earth and the moon. It's at a point where, as the Earth rotates, basically the L2 point moves with it at the same rotation rate, meaning angular rotation rate. So as a result, when you're standing on the sun, once again, you would see the Earth, and the L2 point would always be kind of behind it. And there's a good reason for doing that. It means we can always communicate with it, and it's close. So you draw a line from the sun to the Earth, and 1,000,000 miles beyond that, that's where this is going. That's where the Webb Space Telescope is. There's another one called the Gaia Observatory that the European Space Agency also put up there. So there are several things there already. Now, the thing is, you don't actually want to have it at the L2 point. What's the problem with that? Well, the Earth blocks you all the time from the sun. And so your solar cells wouldn't really give you enough power. So what you actually do is what's called a halo orbit. And that's what's shown in this picture here. You circle that L2 point, and that's reasonably stable. It's a really good orbit. It takes some effort to maintain it, but not much compared to a lot of other orbits. So it's called a halo orbit. They call it a halo because, again, if you were standing on the sun and not frying, and you look past the Earth, and that thing were really lit up brightly, you would see it circling, kind of like a halo. I mean, that's why they gave it the name. It's not an acronym. It's meant to be descriptive. So that's where it's going. It's 1 million miles out. And as I said before, originally it was going to be on a Russian rocket launched by Europe. Typically what happened is most of the Russian launches were actually sold by Europe and launched out of French Guiana, down in South America. So that all fell apart after the invasion of Ukraine. This is a slide actually put out by the European Space Agency here. Pretty much what I described already. It has the timeline, though, on the right-hand side, which is why I included this. It basically says that between 1 and 3 months from now, it just launched this last month, it'll be ready to go. It has to go through a long period. First, it has to get there and get into the proper orbit. And then it has to cool down to even work properly. And just like the Webb Space Telescope, it has one side that always faces the sun. That's where the solar cells are. And then it looks out from that. So it's never going to see the sun and be bothered by that. Since it is an infrared telescope, it really has to avoid all the heat there. And it really has two parts. There's the optical part. It has like a 600 megapixel kind of a camera. And it has a low resolution spectrometer that focuses on infrared. And they need to do that because one of the ways you tell how fast something is moving away from us is the Doppler shift, the red shift, as it's called for light. The faster something is moving away from us, the more the light appears to change in frequency. And so they monitor that pretty closely. And they're pretty much monitoring a third of the universe. They're going to pick maybe something like 10 billion galaxies and take a rough look at that. And then they're going to narrow that down to maybe 1.5 billion galaxies to take a little closer look at. And ultimately, they're going to have a lot of data. And hopefully something will come of that. We don't know that yet. Compared to the Webb Space Telescope, this thing is a whole lot simpler. It apparently doesn't have all those independently adjustable mirrors and didn't have all these things folding out. And it also, just looking at that picture, it doesn't look as complicated on the base. Remember the Webb telescope, you had all these separate layers of incredibly fine metal, and they were designed to just separate ever so slightly so that any radiation caught in them would kind of bounce back and forth and finally work its way out. And this just looks like a much simpler operation. It's not as sensitive. So it actually is not as sensitive as the Webb Space Telescope. And maybe that's part of the reason. But they are being much more effective at looking at much broader portions of the sky much more quickly. So they complement each other. They're not really in competition. Okay, coming a little closer to Earth, Virgin Galactic. Now remember, this is not Virgin Orbit, which went bankrupt, and we talked about them last month and selling off their assets. This is Virgin Galactic. They're the people that have this this thing with a carrier plane taking up a space plane with it. They drop it, there's a rocket on it, and it shoots it off. It's suborbital, meaning it doesn't actually go all the way around the Earth. It doesn't go that fast. They have about 14 minutes from the time you get dropped from the plane. I mean, maybe it takes them a half an hour to get to that point, but from the point they get dropped, they have 14 minutes where it flies up, it goes in, then the engine is cut off and it just kind of goes in an arc, comes back. They end up getting only about 3 minutes of weightlessness, so that's what you get. And that'll cost you $450,000, by the way. So those of you who want to go, definitely go for it, but be aware it's not cheap. They had 3 paid passengers. This is really their first commercial launch. They've done this before. They had problems, and so they haven't done too many. But this is the first commercial one, actually paid by the Italian Air Force and Research Council. It's interesting, they also had an astronaut trainer employed by Virgin Galactic and 2 pilots. So this is very much like a fancy cruise, and the crew to passenger ratio is 1-to-1. That's not a very efficient operation either. Now, what they're striving for, though, is they want to have monthly flights the rest of the year. So that's actually pretty dramatic. Nobody else has done anything like that before. And they supposedly have a backlog of 800 people that want to do this. And probably some of them didn't pay that full $450,000, but that is, if you go to the website, that is the official list price right now. You could sign up. And not only did they get people to sign up, but they've also raised more money from stock sales. So a lot of people are convinced, this one is going to go. Next topic, Starship, which is, of course, the new spaceship coming up from SpaceX. 2 months ago, I was up here and I reported about a brand new use of rotation to split the stages. When the booster finishes, you got to separate from that, and stage 2 has to take off from that. And they worked out a clever way using rotation, just kind of split them apart that way. And, well, they changed their mind. Never mind. That's what they said. So we'll never actually know if it worked because that first test, they didn't actually do the separation. They didn't quite get to that point. They had to, they were terminated. So anyway, maybe we'll never know if this would have worked. There was a lot of controversy about it, needless to say, just because nobody had really done that before. So that's off, and now they're doing what's called hot staging, which really goes back to a method favored by a lot of Russian spacecraft. Hot staging means that as the booster, gets up to about as high as it's going to go, before you release the upper stage, you turn on the upper stage engines, just blast away. And then, of course, at that point, once it gets going, then you turn the booster off. In their case, it has to turn around and then eventually relight its engines because it's going to come back and land. But, there's a short period there where what you see here is both of the engines firing at the same time. That does address a variety of problems that are true with any kind of stage separation process. What the Falcon 9 does, for instance, they just basically turn off the booster, and they kind of push off. They release the clamps and they push off the second stage. And they get far enough apart, then they turn the engines on. And the problem with that is that there's time lost. And every second lost, you're starting to fall back toward Earth. Gravity's pulling you in, you're not fighting it. And so you are losing efficiency in doing this. So Musk actually is claiming as a 10% boost in the payload, which that's pretty amazing. You have to wonder, maybe that other rotational method wasn't quite as good. You must be comparing to that, and maybe there are some other inefficiencies that weren't being mentioned. Now, more details on this, though. As the booster is turned off, they don't just shut the whole thing off. Remember, they have 33 engines. So they only keep the center 3 engines burning at that point, and they only keep them at 50% thrust. So they're really trying to minimize any of the problems. That's why in this drawing, that exhaust is shown as being quite small. And anyway, there's this whole problem called ullage. And ullage is really just a term that means the vapor space above a liquid in a tank. I mean, people talk about that on ships and things too. But the problem you have with the traditional separation, like the Falcon 9 would have, is when everything's turned off, there's no external forces being applied anymore, and the fuel can just kind of float around. So normally, you've had the liquid fuel at the bottom, and that's hitting down toward the engines. So you're feeding liquid to the engines. The problem is once you get in these totally weightless kind of situations, it all just kind of mixes up and you get a lot of vapor bubbles in there. Well, that's bad for a couple of reasons. One is you typically have a pump that's feeding the engines. And people that are here from the oil and chemical industries know that you get cavitation in pumps, meaning those little air bubbles, they cause trouble. One, it reduces the capacity of the pump, but also it actually damages it and then also ultimately snuff out the engine because it's not going to get enough fuel. So that's considered a big problem. So usually what will happen is you have what's called an ullage engine, just meaning small thrusters, that they basically just make sure that you're still pushing a little bit, and as a result, the liquid is still kept down toward the back of the back or the bottom of the rocket. And this solves that problem. The booster itself is providing that, just making sure that you're still pushing a little bit. So that solves a lot of those problems. That was one of the big concerns among people who were reviewing the previous method. It's going to be kind of a mess with power turned off and things rotating. People were not convinced that was really going to work. This removes all those doubts. So anyway, as I said, Musk says that'll have a 10% boost in the payload. There were at least 8 seconds in their current plan for the previous method when there would be no power applied and everything would be slowing down as the gravity pulled it back. Now, there's a catch to all this, though. You do need to modify things. First thing is, the top of the booster, you've got one of the most powerful engines ever built blasting away at it. These are the same engines that tore up the concrete in their test. So that's obviously an issue. They have to put some kind of shielding at the top of the booster just to protect it from the flames, which are literally just coming a few feet away from it. And the second thing is, when you turn on the engines in the upper stage, that's a huge exhaust that has to go somewhere. So they have to have vents, put a whole bunch of vents around the side. And if we look at some of the previous methods of doing this, Titan II, we go all the way back to Titan II. It was originally a missile for weapons use that got adapted for the Gemini program, which is the one that was in between Mercury and Apollo. It's really where they tested out almost all of the stuff that people do in space now, spacewalks, and, docking maneuvers, and all this kind of thing. It goes way back to that. The picture on the right is showing what it looked like when it took off. But if you look closely at the inset here on the left-hand side of the picture, you can see some holes. Now, the circular holes you can see there, those are the obvious ones. Actually, that's not where the exhaust really came out much. Most of it is in those little square areas above it. It's just that you can't see. The way the light is in this one, you can't quite see through it. But anyway, that was used. They made sure there were vents so the exhaust could come out. Yeah, all that weight has to be supported by the parts around it. It's quite a load. These rings that hold things together are very strong. It's actually really more apparent in the Russian Soyuz rockets. And this is going back to 1975, but the reality is they haven't changed their design all that much since 1975. The same kind of a thing. If you look at the left-hand side inset here, you can see the skylight. You can see the blue sky right through it. There's engines up there, or maybe one engine, and it's just basically providing a space. And then you have kind of a conical top so that at least the exhaust coming out of the rocket kind of shoots off to the side, hopefully equally, so not unbalanced and throwing it off course. So there's been a long history of that, but apparently we're going back to it. It's just that now the engines are yet more powerful than they had to be because you're lifting a lot more weight. So it'll be interesting. Musk did say that this will now become the riskiest part of the whole thing. Okay, launches since the last meeting. Well, we already talked about Euclid, so that's a giveaway. But typically I ask, okay, people, how many launches do you think there have been since we met last? Roughly a month, June 10th. 28. You're close, but not that close. Okay, well, actually, I'll give you another clue here. Does anybody recognize what this is? I mean, it's a rocket, but I mean, what is it specifically? What rocket? Yeah. This is the last launch of the Ariane 5, yeah, which is the European launch. It was just launching actually a German and a French communication satellite. Nothing really exotic. It just happened to be the last one. So that is after 27 years. Now, what's interesting is that back in 2012, they started the process for making the replacement for the Ariane 5. It's not here yet. And that replacement, it isn't even reusable. It's kind of sad. They made a decision back then. They thought it was too risky, even though it actually had been demonstrated by SpaceX at that point. It was kind of pretty clearly the way things were going to go.
Oh, it's just a bad.
Yeah, they said that'll never work. Yeah. And then they complained afterwards, well, they were getting undercut on price by SpaceX. Well, of course they were. Yeah. As the old saying goes, if you have to rebuild a brand new jetliner every time you fly to Tokyo, it's going to cost you a lot more. And it's the same kind of argument. Okay, back to how many launches there have been. Actually, it was kind of a slow month. There were only 12. So, of course, even that, you multiply that out. I think the first half of the year we're ahead of last year, and we're on target. I think the second half of the year there will be more. There weren't that many dramatic things that we haven't talked about already.
Launches were Falcon 9s, except for the Delta IV Heavy in the middle.
And what's interesting, of course, is that the Falcon 9 included launching the Euclid Space Telescope, which originally should have been on a Russian rocket that they would have taken a cut up from, but instead they didn't even do that. So, but that's it, yeah. Other space-related videos or slide presentations by me are available at the link shown here. That includes a web page and also a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of National Space Society's North Houston chapter, and the link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.